Howdy, everyone. Happy Monday. Hope you all had a nice weekend. Uh, I'm looking at the picture of me on the video, and I'm kind of glaring, and I've got a westerly sun that I'm trying to block off, so I apologize if it's too bright there. If you look at this slide, this is a good summary of what we talked about last week. We're talking about 6 historical experiments and studies which paved the way for quantum mechanics. And as you remember, a very key element was that the de Broglie relationship, where wavelength is equal to a constant, Planck's constant h, divided by the momentum p, this applies both for electrons and photons. We also saw that you could have the energy of an electron be just the same as for a car, the same formula, 1/2 mass times velocity squared. And we also saw that the energy of photons are Planck's constant times the frequency. So the experiments we looked at, we first talked about atomic spectra. We saw that when you had a certain energy difference between 2 quantum states, and you got emission from that, the energy would come out as photons, where delta E was equal to h nu, h nu being the energy of an individual photon. We then talked about the photoelectric effect. We put energy in, energy h nu. Some of the energy was used up to get the electron kicked off. We call that the threshold energy, and whatever was left went into the kinetic energy of the electron. And then we talked about the Compton and Davison and Germer experiments. Both of them demonstrated the de Broglie relationship. Compton showed that light had momentum by the same formula here, and Davison and Germer showed that electrons and particles also had effective wavelengths given by this formula if you put in the momentum as mass times velocity for an electron. Then where we stopped last time, the 5th experiment, we talked about the black body radiation experiment, and this and the last one are a little bit more difficult to appreciate. But the bottom line was that there appeared to be what people called an ultraviolet catastrophe, that old formulas couldn't explain why the energy coming out did not keep increasing in the ultraviolet range as you went to higher and higher temperature. So it finally took Max Planck to come along and say this could be explained if you assume energy comes in individual packets called photons. You can't just arbitrarily have any energy you want. You have to have these specific photons flying around. So I told you a little bit about Max Planck. He had a lot of unhappy events in his lifetime. And so if you don't remember this from last time, go ahead and read this. I also wanted to show you another picture of Max Planck. And I apologize for this being sideways. But the PDF shower displayer that I'm using right now doesn't have a simple way to flip these. So anyway, this is a special commemorative that I once picked up in Germany, probably, I guess the date here is 1994. But again, if you look up here, you'll see delta E is equal to h nu, and you'll see different colors and radiation and stuff like that. You might disagree, but I think this doesn't make Max Planck look any more handsome than he did in that other picture also. Okay, well, there's one more historical experiment that I wanted to mention. This, again, is not so easy just to understand, but the basic picture to understand, and especially in this course when we talk about statistical mechanics, we're going to find that when we put energy into molecules, and often this is something like heat energy, which is infrared radiation, it has to go into only specific energies. So my picture on the right is supposed to represent all possible energies. So a lot of lines infinitely close together. This is not the way it works. And so again, at the last part of the course, when we talk about thermodynamics and statistical mechanics, we're going to find that energy has to go into very specific units of energy. So what we're going to find in quantum mechanics, each of these horizontal lines represents a possible energy a molecule or an atom can have, and you can't have any other energies in between. So when people studied heat capacities for years and years, and maybe you're still using this in chemical engineering, the law of Dulong and Pettit was used. And this works most of the time. This basically says heat capacity at constant volume is 3 times the ideal gas constant. I've said here that it only holds at high temperatures, but I really should have written at just the opposite. It holds except at a very low temperatures. So here we have temperature. Why I paused there, I was confused by seeing the T in a funny direction. Temperature here is increasing to the left. So if you go to real low temperature, the law of Dulong and Pettit fails, and you see that the heat capacity actually drops quite a bit lower than just the 3R value that you would normally have. Well, it turns out, this was explained by the model that we have up here, that it has to go into specific energy levels. Maybe you've learned this in chemical engineering, but the classical view, according to Dulong and Pettit, the argument was that if you have capital N number of molecules, and they each vibrate in 3 different directions, the total energy would be 3 capital N kT, K being the Boltzmann constant. And if you convert this over into ideal gas units, and maybe you've seen this in chemical engineering or not, but Avogadro's number times the Boltzmann constant is equal to the ideal gas constant, you would get that total energy is 3RT. And heat capacity, of course, is how much energy you have to put in per degree, and that comes out to be 3R if this is what you assume to be the internal energy. Well, it turns out the real formula looks like this. This was explained by Einstein and Peter Debye, who's probably the most famous American physical chemist. And it doesn't look anyway that this could come out to be 3R at high enough temperatures. But if you expand these exponential terms in Taylor series, put it all together, make T be really high, you basically wind up that all of this stuff just comes out to be 1 and comes out to be 3R. Anyway, we don't need to be familiar with all the details of this, but the main point was that light came in quanta, and they had to wind up going into specific energy states. And as I keep repeating myself, when we get to the last part of the course, we will see how this works as we put energy into the different quantum states of molecules. Okay, well, this brings us to the key point in the whole course, which is the Schrodinger equation. We're going to be solving this a lot for various kinds of systems. As we'll see, Schrodinger is going to claim that anytime we know what the potential energy is for a system, and usually we do, we can get everything there is to know about the system if we solve his equation. Before we go on with that, however, let me try taking a poll. I tried this last time and wasn't ready. So can everybody see this poll? Somebody answer me?
Yes.
Yes.
Okay, so please do it. there are 4 questions. Can you scroll down to number 4, or do I have to do that?
We can.
Okay. Okay, about half of you have answered at this point. Okay, I'm not seeing any answers, so I don't know if you can see the answers yourself. I hope so, but 67% of you were born in Texas. 42% have been to Europe. That's impressive. 27 have been to Asia. That's usually a lower number. And only 2/3 enjoyed the Orange Bowl. I guess that means the others aren't football fans, or somehow you wound up here rather than UC LA or something like that. Okay. Okay, this was just a test run. I may want to do some other polls in the future. So I'm just learning more and more about Zoom as we go along. Okay, well, thank you all for answering. So back to the Schrodinger equation. You'll see his name spelled with the umlaut O with the 2 dots on it, and we should pronounce it Schrodinger. But very often in textbooks in the US, we'll change the O umlaut to an OE and just say Schrodinger. And here's a picture of Schrodinger on an Austrian stamp. This is way back when the Austrian money was still shillings. Now they've gone over to euros. At this time, I think it was about 11 shillings per dollar. So this was about a 50-cent stamp. And then I have one more picture of him. And here Schrodinger is on the 1,000 shilling bill, which is worth, at the time, was worth almost $100. So I don't know if that's a compliment to Schrodinger because he's on such a high denomination, or since very few people ever had 1,000 shilling bills, maybe it's kind of put him out of the way. Anyway, you'll see Schrodinger here on the money has the wave function psi that we're going to talk a lot about. This is a Greek letter psi, and so that is going to represent what we call wave functions for these Schrodinger equations. Okay, so remember at the beginning I told you this course was going to be about energy and waves, and we see all of that in this one equation. And we're going to find that this gets fairly complicated, but we're dumbing this down absolutely as far as possible. So I'm starting off giving you this equation for one particle in one dimension. And so that dimension is going to be x. Now, if you think about it, if you just, let's look at the water molecule. If you look at the electrons in the water molecule, it's going to have 12 electrons. Each requires 3 dimensions, x, y, and z, to describe where it is. So that becomes a 36-dimensional problem. So you can see how much we're simplifying the problem that we're actually going to look at. Nonetheless, we're going to see there are real cases that this equation is going to be useful. If we have vibrations of diatomic molecules, we can just have a single potential energy in one direction of vibration. We'll also find that it works for rotational spectra of diatomic molecules. And we'll also see that it works for translations of particles, or just particles flying around in space. Okay, as we saw last time, total energy is always equal to potential energy plus kinetic energy. But now we're writing it a little bit different. So again, last time I wrote that you could write kinetic energy as p squared over 2m. So you'll notice the 2m is still here, but the rest of this represents the momentum squared in a differential form. And we'll see how that works. Second term is just the potential energy term. Capital B will represent the potential energy term. If we had the harmonic oscillator that I mentioned last time, it would be 1/2 kx squared. Okay, so the way that this equation works is we stick in a functional form of the potential energy. It can be zero, it can be a constant, or it can depend on x. And then we solve it. And when we solve it, we get a large number of solutions for capital E. E will represent the possible energies that that system can have. These are what we're going to call the quantum states. When we go to solving the hydrogen atom problem, the capital E will represent the energies of the possible hydrogen orbitals, for example. Now, along the way, when we solve for capital E, we're going to get a corresponding wave function psi. And so we saw this Greek letter psi on Schrodinger's 1,000 shilling money. And so this is going to carry the wave properties of the system. And this psi is also going to tell us about the characteristics of that particular energy level. From it, we're going to be able to calculate average momentum squared, average position. We're going to find that we're never going to know exact positions of electrons and protons and molecules. We're just going to be able to calculate their average positions and their distributions. Okay, so everything is defined down below here. Psi is a function. So psi of x means it's going to depend on x. It's what we call the wave function. And as I'll mention again on the next page, we'll also call it a characteristic function. Capital V will also be a function. It can depend on x. The capital E's, there's going to be many solutions. These are going to be quantized. The symbol h bar here, just for simplicity, this is Planck's constant over 2 pi. We call it h bar. We run into this over and over again, so a lot of times we'll just write h bar squared here instead of having to write h squared over 8 pi squared, actually, as it turns out to come out. M is the mass of whatever we're talking about. Again, capital V is the potential energy, x is going to be our coordinate. And I made a note here that this is considered to be a law of nature, just like Newton's F is equal to mass times acceleration. Okay, so more about this problem. The Schrodinger equation is a type of equation known as an eigenvalue problem. Eigen is the German word meaning characteristic. And for this equation, as I said, there are many, many solutions of capital E, the energy level. In fact, there are an infinite number of solutions. But don't be confused by this. That doesn't mean that every possible energy works. And so by analogy, think about the fact that if I ask you to tell me how many integer numbers there are, the answer would be infinite. But the integers would not contain all the possible numbers. You could have 1.37, you could have 2,768.4. There's lots and lots of other numbers that would have to be there if we had the total set of numbers possible. So in the same way, the Schrodinger equation can have an infinite number of solutions, but we're only going to be interested in specific numbers of those, and lots of values, in fact, even more values than our solutions, will not be valid. In case it makes you worry that I might ask you to give me an infinite number of solutions, the good news is we'll usually have a fairly simple formula. And in cases where we might not, we might only be interested in the lowest energies of a system. So when we go to talking about molecular vibrations, we will never be interested in, say, even 100 solutions for the vibrational problem. We're mostly interested in one, maybe sometimes 3 or 4 or 5, but we're going to be interested in the lowest energy solutions. Okay, well, every time we solve the Schrodinger equation and we look at one of the solutions for the energy E, we also get a solution for psi. This is the Greek letter psi. And this is called the eigenvector, or simply the wave function that we have. And as I already mentioned, this will be used to determine the properties of a particular energy state. So that's for the values of the coordinate, the momentum, etc. Just to show you quickly how this can become more complicated. If we had our one particle now, like our one electron in 3 dimensions, the second derivative term with respect to x now expands to including y and z. So we'd have second derivatives with respect to x, y, and z. So this becomes the Schrodinger equation. And note that I'm saying psi is now a function of all 3 coordinates, x, y, and z. Potential energy can be a function of all 3 coordinates, x, y, and z. I'm going to mention this many times, but make sure you write it down in your notes. Whenever we do solutions and you get a solution for capital E, it is not a function of coordinate. So capital E will be some value that you can calculate, and it will be a possible energy for the system. When we get the wave functions, they are going to remain as functions. Okay, so we've got this started, but now we want to go a little bit into nomenclature. And we're going to use something called operators quite a lot in this course. We get tired of writing derivatives or sometimes even multiplying things out that include derivatives. So to start off, we're going to write the symbol, a little triangle here with a square on it. We'll call this del squared. And this will be an operator. This is what the operator looks like. And what it means is it operates on whatever follows. So look at what we have up here in the 3-dimensional one-particle Schrodinger equation. Instead of writing this out in its entire form, we can write the equation out in much simpler form. We'll just write it as del squared psi. So I hope all of you can understand this is exactly the same thing as that, because the del squared operator then operates on what follows, and we wind up taking second derivatives with respect to psi. Okay, so this is exactly equivalent to what I have above. Now, to try to confuse you a little bit more, when we do it this way, you see we're still left with a h bar squared over 2m over there. And so we'd like to make the equation look even simpler. We're going to write what we call the Hamiltonian operator. Another name for this is the energy operator. And you'll see the Hamiltonian operating on psi is equal to E psi. So this H psi represents exactly everything that we have here. We multiply by minus h squared over 2m, plus we take these second derivatives. Now, if you go to the physics and chemistry literature nowadays, and people write an article on quantum mechanics, they will start off and say, we're going to deal with the Schrodinger equation, just say h psi is equal to E psi, and it looks very simple. And then it gets complicated when they write the next equation, because what they will do is they will define what the Hamiltonian is. Keep in mind, this was only for one particle. So if we go to the 12 particles, as I said, we would have for the water electrons, this would become 12-dimensional, and you would have 12 terms in there. So this journal article that I'm talking about would have to have 12 terms showing you what the Hamiltonian is. But basically, it's always understood we go back to this formula. Another reason for writing this general Hamiltonian operator is we're sometimes going to find it's more useful not to work in Cartesian coordinates, x, y, and z, but we might want to work in spherical or polar coordinates. And you remember that we have these relationships here between spherical and polar coordinates. I think on my next slide I have here a Cartesian coordinate diagram, z, y, x, but we can also define in terms of the distance r from the center point, and then two angles, theta and phi, for the spherical coordinates. Now, fortunately for us, we're not going to have to use spherical coordinates very much because you can see it starts getting pretty awful. However, when we get to talking about the hydrogen atom, for example, it's going to be a lot more useful than Cartesian coordinates because we can put the nucleus at 0, 0, 0 here, and then we can take the distance r as being the distance the electron is from the hydrogen nucleus. So for now, I just want you to be aware that this exists, and maybe you even saw this when you went through your calculus courses, but you can see it gets to be much, much more complicated. You have first and second derivatives with respect to r, you have first and second derivatives with respect to theta, and then second derivatives with respect to phi here. Okay, so this is now the background of the mathematics that we're going to be talking about. Let me just read this last statement on this page here. For atoms and molecules with more than one particle, 3 coordinates per particle have to be considered, and the Schrodinger equation becomes even more complicated. So it turns out, ever since the Schrodinger equation came about, the main problem has not been knowing what the potential function is, but the problem has been in doing the math. In our course, we're going to talk about some simple systems that were solved early on, but larger systems like wanting to know what is the structure of benzene, they get much, 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 much more complicated. And if we didn't have computers, we could really not get the answers. Most solutions to the Schrodinger equation are numerical approximations, but the computer programs have gotten so good that nowadays, for all practical purposes, they're almost just like exact answers. Okay, so tell you a few more things about the Schrodinger equation. It says, if we know the potential energy for a particular system, and I've written we often do, a better statement would be we do most of the time, we know what the potential energy function is. We can, in principle, use it to solve for all the possible energies of this system. So, in principle, this always works. In practice, it depends on how large the problem is and whether our computers can handle it. Nowadays, even big chunks of DNA can be done by the Schrodinger equation, but a lot of times even supercomputers may take days and days to calculate out the possible answers. Okay, well, here's the however. For a system with n particles and 3 n coordinates, the mathematics for solving the equation can quickly become overwhelmingly complex. So, as I'm repeating myself for the umpteenth time, much of quantum mechanical work is involved with finding approximate mathematical solutions for the Schrodinger equation. Computers help. And they help immensely. And keep in mind, when I say approximate solutions, they might be right to the first 6 or 7 decimal places. So computers and numerical techniques can be very powerful. Okay, so this is where we're going to start from. I do want to tell you another bit of good news, which is we're going to stick to what's called the time-independent Schrodinger equation. As you know, Einstein said we live in a 4-dimensional world, X, Y, and Z, and also time. But we're going to stick to 3 dimensions. It turns out time-dependent forms of the Schrodinger equation are important if we want to look at chemical reactions, dynamics, transitions from one quantum state to another. But that's beyond the scope of an undergraduate course that we have. Students who get into graduate courses on quantum mechanics will cover this. Basically, when you do the time-dependent form, then h psi is still equal to E psi. The difference is that you now write the energy differently. It becomes I h bar, and then the derivative of time with respect to the wave function. So we're allowing the wave function not only to depend on x, y, and z, but also depends on time. And notice here, I is the square root of -1, the imaginary I. Some of our solutions of the Schrodinger equation will involve complex variables. I assume most of you have not had a complex variable math course. That's not a big deal as far as we're concerned, but we are going to get some solutions that are going to have an imaginary I in it. If you haven't already encountered it, complex variables and imaginary I's can be very useful. We have spectrometers called Fourier transform infrared spectrometers. You get a real part and an imaginary part that comes out of the solutions. And both of these help you figure out really what's going on spectroscopically. Okay, but this may be the last time I mention the time-dependent Schrodinger equation. I might mention a little bit later if we talked about chemical dynamics right at the end of the course. Okay, I have a chat question, or at least there's a chat comment from somebody. Okay, I've got so many people thinking ahead. Someone says, how does Schrodinger's equation take into account the Heisenberg uncertainty principle? Well, I'll tell you this again. Basically, as I've just written, or wrote on this page, if we know the potential energy for a system, we can in principle use it to solve for all the possible energy states of the system. So Schrodinger basically says, if you solve his equation, you can get answers to everything you might possibly want to know. Heisenberg is going to throw a wet blanket on this and says, we can't know everything. And so we'll come back to that when we get to the Heisenberg uncertainty principle. Probably we won't get to that this week, but no later than next week, we'll talk about Heisenberg. All right, this next page I used to not have in my lecture notes, but I've stuck this in just for the fact that then maybe you can have a better sense of what the mathematics is like for the problem. I think I promised you last week that I would not make you solve a Schrodinger equation like this if I give you a potential energy, but I might give you the solutions and ask you to show me that they are indeed solutions. So just for simplicity's sake, we're going to take our one-dimensional particle. We'll have it just flying around in free space. And so we'll say the potential energy is equal to some fixed potential energy. It could be zero, as I'll later have in another example. But here I'm just going to call it capital D sub C. And I'm going to ask you to test whether this wave function, sine of kx, is a solution. Now, obviously, I must have some motivation for picking this as a function, but let's go through the process. So the Schrodinger equation says, let's take second derivatives of it. Derivative of sine kx is k cosine kx. We take the second derivative of cosine is minus the sine, and so we get a minus k squared sine kx. So let's plug that back into the Schrodinger equation, and you'll see this is what we have. The sine kx's cancel out, and we get a solution that is not dependent on the coordinate. So I already mentioned this, but drum this into your head if you're doing a problem. If you solve for an energy level and you get an X dependence, you messed up, you made a mistake. There cannot be any coordinate dependence in the energy solution. Okay, so notice that the energies are dependent on the initial potential energy, and they're also dependent on this constant K that I stuck in here. When we go on later in the course, we'll see that there are some reasons for picking particular Ks and not picking others. But for now, all we know that it is a constant. But when we introduce some of the wave properties, we're going to find that we have something called boundary conditions that will dictate what the K values are. When you took freshman chemistry, you learned about the atomic orbitals, 1s, 2s, 3s, 3p, 3d, so on. The 1, 2, and 3 there represent quantum numbers, and the K here in this formula would wind up being a quantum number. So we haven't put any constraints on what our K is in this problem, but we will later on. But now notice that there will be an infinite number of solutions, even after we make K to be an integer, because any integer here could work. We could have K be 1 or 2 or 3, or in fact, according to this equation, it could also be 0. And so there are an infinite number of solutions, but many values of K would not work if they don't satisfy the other conditions that we will dictate later. Now notice also, this was our wave function. So let's say we pick K equal to be 3. So our wave function would be the sine of 3x, and that would correspond to our energy solution where K is 3 here. We'd have 9 h bar squared over 2m plus Vc would be a particular quantum state energy, and that would have the wave function sine 3x that goes along with it. If we pick K to be 124, it's still a solution. We have a much higher energy, the wave function is changed, and the energy level is changed right here. Okay, I'll try now to give you some more sense of what we learned from the wave equation. The solution gives us many values of the energy E. Each E represents a quantum energy state of the molecule. Any other value that does not come out of the Schrodinger solution does not work, and the molecule or atom or whatever system we're talking about might be a free electron. It cannot have any other energies. And so each of these energies is called a quantum. It's a quantum amount of energy. And this number 2, I've already said, each value of E has a corresponding solution for the wave function psi. Each psi characterizes the behavior of the particle or atom or molecule or electron, whatever, in that particular quantum state. So make sure you understand these solutions come in pairs. If I solve for E sub 3, then it's going to have a wave function psi sub 3. And they will both be different than solutions when I, for example, on the previous page, pick K to be 7 and maybe have solution E sub 7. Now later on, we're going to talk quite a bit about the harmonic oscillator. But let me just show you what some of these solutions are, and so you can appreciate what they might mean. You probably learned about this in physics. We have a particle hooked by a spring to an infinite mass. So think of this as a brick wall weighing 10 tons. Our poor little electron weighs 10 to the minus 40th tons or something like that. So the brick wall is not going to move while this vibrates. And we can say the force is minus kx. If we go to minus x, it's a positive force trying to make it go out. If we go to plus x, it's a minus force trying to pull the spring back. The potential function, the potential energy function for this is capital V is equal to 1/2 kx squared, where k is, in this case, called the spring constant, or when we get to talking about molecular systems, we'll call them force constants. And we're going to find that those force constants are proportional to the strength of a chemical bond. So as I show here, chemical bonds are going to be similar. If you hook two atoms together, say it's got a spring constant or force constant of K, that's the representation that we have. All right, so this is what the harmonic oscillator Schrodinger equation looks like. Notice we've stuck in the 1/2 kx squared. We'll look at a lot of these, we'll look a lot more at these solutions later, but just for now, I'm going to give you that the energy levels are given like this. This is a little v, not to be confused by my capital V up here, and I apologize for that, but that's the convention. The little v will be a quantum number that can be an integer, any integer starting at 0. You can have it be 0, 1, 2, 3, all the way up. If we talk about vibrations, we typically don't care about any quantum numbers higher than about 10. So even though there are an infinite number of solutions, we're only going to care about a few. In this expression, nu, again, represents a frequency, and for a harmonic oscillator, the frequency is 1/2 pi times the square root of k over m. I've written this as k over m to the 1/2 power, which is the same thing. And notice, just for nomenclature, I write these as E subscript V, and V is going to represent which energy state we have. Okay, so the lowest state, when V is equal to 0, is called the ground state. And we're going to have ground states for all our quantum mechanical problems. And you see, according to what I've defined up above, it's 1/2 h nu. Mathematically, it comes out to be h bar over 2 times the square root of k over m. Notice the 2 pi went into the h part of the problem, and so this is why it comes out to be h bar over 2. And if you use that formula, you'll see the next level is at 3/2 h nu, next one at 5/2 nu, next one 7/2. So they keep having separations of 1 h nu. Okay, well, we also get solutions for the wave functions. So if we're in energy state E0, which has energy 1/2 h nu, the wave function psi naught, psi 0, it's going to have a constant in front, and we'll talk about these so-called normalization factors later, but it'll come out to be e to the minus 1/2 alpha x squared. So this set of wave functions are just about the nastiest that we're going to run into, but that's okay. We can get used to this right now and then look at simpler problems later. When we go to the first excited state, as we call it, the lowest state is called the ground state. E1 would be the first excited state, E2 would be the second excited state, and so on. Psi 1, the wave function for the first excited state, gets even more complicated. It's got an x term, more stuff up front, but it's still e to the minus alpha x squared over 2. And notice we try to make it look simpler by putting a definition for alpha. So if we wrote all this mk to the 1/2 over h bar here, this would really look like a messy, complicated solution that we have. Okay, so we still have time to do this today, and this is what I wanted to show you. Basically, if we put both the E0 and psi 0 into the Schrodinger equation and solve it, we'll find that the two sides of the equation are equal. What I'm actually going to do is I'm going to take the psi 0 solution, plug it into the Schrodinger equation, and then demonstrate that this is the energy level that we get out of the system, or actually look like this right here for E0. So we're going to go up here. I'm going to take that solution for psi 0 and put it in, and we'll see what we get for capital E. And if we do our math right, that capital E should not have any X dependence on it. Now we could also do it for psi 1. I'm not going to do it for you. You can do it for psi 2, psi 3, etc. But the math gets really pretty hairy. So for today, let's just be content with doing psi 0. Okay, so we need to find the second derivative of psi naught. So here I'm taking the first derivative. And this will be the nastiest derivative you have to take. We all remember the derivative of e to the minus x would be just minus e to the minus x, or the derivative of e to the minus ax would be minus a e to the minus ax. But here in the exponent, we have an x squared. So the derivative of this is going to be the exponential expression itself, plus then we have to take a derivative of what's in the exponent. And so that gives us a minus 2 times a half alpha x when we derive this. I put the same problem in your practice math self-test, which is right at the end of the syllabus if you want to look at that again. But make sure that you're familiar with doing this particular derivative. This is, I would contend, the only really difficult derivative you might have to do all semester. All right, so hopefully everybody is convinced. We do the first derivative, we get the minus alpha x out of it. To take the second derivative, what I'm going to do is I first fix the minus alpha x, and then I take the derivative of the exponential term again. And so I get another minus alpha x out of it. And then I'm going to fix the exponential term, and then take the derivative of minus alpha x, and I get the minus alpha out of it. So I put this all together, this is what we get. And you'll notice that in front here we have this, and that was the wave function psi 0 to begin with. So when we plug it back into the Schrodinger equation, we can make it look a little bit simpler by putting this whole business here in front of psi naught. Now, you'll notice that psi naughts cancel out, but we're left with a problem that E naught has a 1/2 kx squared dependence on it. But we haven't yet plugged in what alpha is. And I won't belabor this in class, we're running out of time. But if you solve for what alpha squared is, then you get mk over h bar here. And alpha here is just plugging it in there. If we combine all of these terms, you get a minus 1/2 kx squared here. It cancels out the plus 1/2 kx squared. And we do get our E naught solution for the harmonic oscillator. And this is identical to what I told you the answer would be, which is right here. So probably on your first hour exam, you might expect a problem like that I might give you a wave function for a particular state. You can cross your fingers that I won't ask this for a harmonic oscillator, but I might ask something else and want you to show me that what it is a solution to the Schrodinger equation. And note, when you do this, you also immediately get a solution for what the energy level is. So this is basically our result for the harmonic oscillator. These are the possible energy levels that we have. When quantum number little v is 0, we have an energy of 1/2 h nu. We go up to v equal 1, it becomes 3/2 h nu, then 5/2, 7/2, 9/2. All of these spacings are just h nu. So E0, E1, E2, E3, E4. Now notice the lowest energy is not 0. So the lowest possible energy the system can have is called the 0 point energy. And again, as I said, it can't be equal to 0. So later on, when we start talking about molecular vibrations, it's going to seem crazy but you can never stop molecules from vibrating. They're going to keep on vibrating. They will always have at least this minimum amount of energy. And this won't be the only problem that will have 0-point energies. I have a chat question. Let's see if it's relevant. Rachel asks, how do you find the corresponding psi values? Those are solutions for the Schrodinger equation, and as I promised you, I would not make you do that. So when we're going to look at particular solutions, like I just did here for the harmonic oscillator, I will typically give you at least the wave function and maybe wave function and energy levels. But for this kind of problem, I give you the wave function and you have to find then what the corresponding energy level is. Now, to emphasize again, if I took the wave function for psi1, I would get E1. If I took the wave function for psi4, which I'll give you formulas for later, you will get E4. So every individual wave function will give you a different result. Well, we've more than run out of time. Just on this page, note this is what the wave functions look like. And next time we're going to talk about what we can learn from looking at the wave functions. So you can send me some more chat questions or ask some orally, or you can just take off. Okay, thank you all. Have a good week.
You too. Thank you.
Take care.